Hey guys, how's it going? Wasn't originally planning on filming this for you, but we had a good class today where we talked about what you'd be doing this week with circles. So circles, at the end of the week, you're going to have to go from something called the general form of a circle, the general equation for a circle, to its graphing form. So you're going to learn two different forms of an equation for a circle and how to go between the two. And when I previewed that, I actually got some good questions in class. I know that Yushi and Casper were talking there on the chat, and it sort of led its way to something that I wasn't planning on talking about, but it's something that I actually do usually talk about during geometry because I think it's just more or less a good heads up. You kind of come back to this near the end of Algebra 2, and you do a bit of it in pre-calculus, and so it's kind of good, interesting to know what to kind of expect here. So, anyways. Putting this into pictures, and I remember Casper's like, huh, what? Conic sections? What is this guy talking about? But this is kind of what I was trying to talk about when I was talking about the equations of a circle versus if you make some changes to the equations of a circle, you actually get slightly different shapes here, okay? So looking at this here, this is the general equation for a conic section. And one thing that Yushi noted on the call when I just happened to show you the general form of a circle very quickly, is that the amount of x squared terms that you have for a circle's equation is going to match the number of y squared terms there would be of an equation. Okay, so let's maybe look at this at Desmos, what I was trying to show you here before. So it's something very simple. If I have x squared plus y squared, and then maybe I add on a few of those other terms that appeared there a second ago, 4x plus, or maybe we'll do a minus for the heck of it, minus 6y. And then do something with a constant, maybe like add a constant here and set it equal to 0. That's more or less pretty close to this general equation for a conic section thing here. I'm going to skip this bxy thing here just because I don't want to deal with that at all. But anyways, I get a circle out of this, okay? So the big thing here is if I have the same number of y squareds and same number of x squareds, I get a spherical circle on the graph, and you're going to learn why that's the case later on this week in your studies in coordinate geometry, okay? So another thing too that they make write down, and this isn't important for your work at all this week in coordinate geometry because your a is always going to be 1 here. So remember, for a circle, you'd have to have the same coefficients for the x squared term and the y squared term to make a circle in the graph. So if I put like a 3 here and a 3 here, oops, what happens? A circle move. Well, 3 is not a good example, I guess. What about 4 and 4? Is that going to work? I got it to work yesterday in class. I don't know. Something's going on here. Maybe I need to change something with my constant. I don't know. Yeah, there we go. And we changed something with my constant. I got a circle. So something. Maybe my radius wasn't big enough or something like that in the situation here. But anyways, you can change around. Let's see if I can get 9. Yeah, so it's just to prove to you that it didn't all have to be even coefficients. Anyways, as long as your a values are the same, or your not a value, let's get away from the discussion of a value. As long as your a equals your c, for instance, here, right? Same number of squares you have is y squared. You're going to get a circle on the graph as long as you get some sort of relationship on the graph. Okay, this is going to change if you change, right, your coefficients of either of these, right? They're different from one another. You get something here that's called an ellipse. Yep, this is called an ellipse here, which is actually featured right here. So I figured I'd show this to you as a heads up that, guys, cones are going to come back, right? They're going to come back to you late in Algebra 2 and in pre-calculus and beyond. But cones are interesting because you can do there are a lot of similarities in equations of the features that get created when you run a cross-section through a cone itself, okay? So you might be trying to remember what a cross-section is because that's a relatively new thing from geometry right here. But a cross-section is if you take a plane, right? So you take a plane and you run it through a solid, okay? And where it intersects more than one point of a solid. So a cross-section wouldn't be tangent to the apex, for instance. That wouldn't be a cross-section. But a cross-section would be like right below the apex. And if right below the apex you ran a plane that was perpendicular to the base, perpendicular to base, you would get a circle, right? You get a circle here as your intersection with the cone, and the plane would be a circle. And in fact, I guess it would include the interior, right? Because a solid includes its interior, unlike a shape itself. But anyways, we're just worried about the circle here. Okay, so if you tilt that plane at all, right? If you tilt it at all, you get a different shape. So here, the cross-section of a cone, when you run a plane through it, that doesn't touch the base at all, but right, we just tilt this plane maybe ever so slightly, tilt it up here and tilt it so it's going through. So it's going to go through one guess part of the lateral surface. So it basically only the criteria would be it would only intersect the lateral surface, not the base, and it would not be parallel to the base of the cone. You get something called an ellipse, which I think you know a good word for ellipse, right? What could you call an ellipse if you're speaking like a normal human and not some crazy math robot? Yeah, that's right. It's a cone. Sorry, not a cone. It's an oval. What am I talking about here? An oval. Okay, so an ellipse we can kind of think of as an oval, and that follows pretty much the same general equation. The only difference is that you have different number of x squareds and different number of y squareds, and you'll learn stuff about this in algebra too. I'm not really going to go into it. So it'll be wider if there are more y's than x's. So if I make this more x squareds than y, sorry, x squareds rather, right? More y squareds than x squareds would be wider, but if there were more x squareds than y squareds, we're going to be taller here, right? We're going to have a greater vertical distance from across the ellipse here. So anyways, that's sort of an ellipse which we'll study. And I'm actually going to go into a lot more about this stuff later because there's some interesting stuff that comes in here. And the reason why they just get studied a lot more here. Okay, parabolas. Yes, parabolas actually come up with cones. Here. So a parabola, you might want to notice this, it's a little bit hard to see here, but this parabola, I'm going to draw it like this. This parabola is on a plane, okay? So the plane that intersects is parallel to the lateral surface, okay? Parallel to like the lateral surface on the other side. So I shouldn't really say parallel. We should maybe write it a different way, but the plane has the same slope. Okay, same slope. If we consider the slope being maybe like the base of the cone here as like the x-axis, right? Consider that to be like our x-axis right here. This parabola would have kind of the same rise over run as the lateral surface, right? As the cone itself, you might say. You might see this in textbook written, but as the lateral surface. So this here, this rise over run, same as this rise over run, okay? And if you run a plane that's parallel or at the same slope as the lateral, it isn't really lateral edge, it's kind of like the slants, I guess, here, you're going to wind up with actually a parabola. A parabola gets formed. That's your cross section right here. So here's where a parabola is naturally occurring in the wild. It's not just some weird thing that you study in Algebra 1. You might be running like, hey, why does that matter? I'll show you something about parabolas a little bit later in this to make sure why it matters, okay? Then if it's not a parabola, right, if the slopes aren't exactly the same going through, if the slope is actually steeper, okay? So with hyperbolas is actually a distinct figure. You might think this looks kind of like a parabola right here, but a hyperbola, it's pronounced hyperbola, this has a steeper slope or a greater slope. Okay, than the lateral edge or the slant height of this cone is here. It has a steeper slope. Okay, the plane has the same slope as the cone, and the hyperbola's plane has a steeper slope than the cone. That would be the cross section you would get if you ran a plane that was steeper, right? Steeper than the way that this is going. As you see, this cone here is flat, like this is just shooting up high up into the air. Okay, something called a hyperbola, which we'll get to in a second. Okay, so anyway, this is actually right. General equation for a conic section. Hey, if I change this, actually, how can I change this equation to a parabola? What would I do here? Because you guys have been studying parabolas a bit now. So maybe let's look at Desmos, and then let's look at this slide and think about how we would change the general equation for a conic section into a parabola. What would you do? What are the parabola equations you've seen look like this so far this year? Oh, that's right. You've been doing quadratic functions, right? Quadratic functions make a parabola on the graph. So with that, that's a relationship between x and y, right? What is in there? What else is in there? Oh, right. X squared's in there too. Is y squared in there? No, it's not. Okay, so let's go ahead and let's axe this squaring thing, and let's see what we get. Oops, I did that. I had an extra space there. Oh, there we go. Okay, so I got rid of the y squared. Now I just have x squared right here. Right, I just have x squared. I no longer have y squared right here, so I could just combine like terms, get rid of that plus 1y, make it negative 5y. So here we go. Right, this is a parabola here. Okay, so this is if we ran a plane parallel or the same slope as the actual cone itself, the actual party hat running through. The intersection with the cone, the surface of the cone at least, would be a parabola. And the region in the interior would just be the interior of the parabola here, okay? And then last one is hyperbola. And hyperbolas are going to look pretty crazy to you. I'm going to show it to you. It's going to look kind of crazy, but you might be wondering what makes a hyperbola. Well, let's go ahead and put a squaring thing on here. And the one thing that we haven't really done yet is get a relationship. Oops, sorry, that's still a parabola because we just had x there. So, okay, so here we have an ellipse. So we have 2x squared plus 4y squared. And I'm going to change this to a minus sign. Boom. And here we have a hyperbola. We have a hyperbola over here, and we have a hyperbola over here. This actually might be technically one hyperbola. I don't know. It's been a while since I studied these. There's a lot of stuff in here, so you got to stay focused throughout all this. But anyways, now you're just getting just a tiny bit of familiarity from this. Okay. So what I did here, right? I subtracted it, right? So I just changed the signs here. I did 2x squared and then subtracting 4y squared. That's usually an indication that you're going to end up with, right? So if C here, right? If C here is negative, all right, negative, it's likely going to be a hyperbola. Okay, so just a few things going on here. Okay, so to summarize, I guess what I put here, A would equal C because we have A here and we have C here. To get an ellipse, A doesn't equal C, but they're the same sign. And you'll learn the underlying math, I hope, about this. It's been a long time since I've studied this. Maybe you won't. Who knows? Underlying math about this in Algebra 2 and in pre-calculus and beyond. A doesn't equal C. It's the same sign. And then you get a parabola, right? If it's just, if you have an x squared, no y squared. So what I could say there is just like C equals 0. Okay, and you get a hyperbola if your C is negative, right? If your C is negative, you get a hyperbola out of that. Okay, so just a few brief things about conic sections, right? And getting used to this. Part of the reason why I assign you that those Thursday and Friday assignments, even though it's not in your textbook, right? The big thing is really just that PSAT question kind of spooked me when I saw that. I was like, why is this here? Because not many people don't know how to do this. So I've assigned it, and I'm sticking to it. I think it's a good thing to do to learn how to manipulate equations, right? How to take the general form of the equation of a circle and change it into the graphing form by completing the square. But also, this gives you a heads up to what you might be doing in Algebra 2. So you just get into this, like, whoa, this is way more dense than I was expecting it to be. So anyways, just a little bit things to look out for a little bit later. So let's look at another slide here, just another demonstration. Oftentimes when you study these conic sections things here, right, I had no idea why we were talking about cones, right? I legitimately, in high school, these textbooks didn't really have pictures. Like, we didn't have Desmos, we didn't have PowerPoints even. It was just sort of like, hey, we're studying conic sections for like the 4th week in a row. I'm like, what the heck does like an equation like this, honestly, like an equation like this, what does it have to do with a freaking cone? What does it have to do with a freaking cone? Well, you're proving it, the stuff about circles at least, the cross-section of a cone with circles, you're proving that in geometry. And actually, maybe a little bit you're looking at kind of parabolas in Algebra 1, because if you don't have this term, right, it becomes a parabola. And you should know that. We have x squared here. We have a y term there, right? Let's just ignore this for now, this xy thing. And then ellipse and hyperbola you're looking at later. Okay, so when you're squaring x's and squaring y's, like, things happen, right? You actually get shapes that all are naturally occurring within cones. So stuff to look at here. Notice the parabola, the slope of this lateral surface, this slant here, I guess is what you call it, on the cone, same as the parabola itself. And note that because of this, a consequence of this, and it can't be, right, obviously, if you're tangent to the side of the, it wouldn't be tangent. I mean, if you intersected this, I guess, would it be tangent? No, it would be tangents. Yeah, it wouldn't be tangent because you're touching more than one plane. But anyways, if the plane is on top of, it contains like the slant, obviously that's not going to be a parabola. It's just going to be intersection will be a line at that point. So it's got to be sort of got to go through the base, the interior of the base here, not just the edge. And because of that, a consequence of that is that that plane that's parallel to the slant of the cone is only going to touch one of the two cones. It's actually called a double cone, believe it or not, right? This is a double cone. So when you study conic sections, oftentimes you have diagrams that look kind of like this because the odd man out is this hyperbola, and I'll get to the hyperbola a little bit later. But if you remember, the hyperbola had kind of a weird graph right at the hyperbola right there. What's going on? So hyperbola comes in pairs, and we'll think about that in a second in terms of like the actual geometry of it, and why it comes in pairs. Why we have this, and then it's the rest of the hyperbola over there. And a parabola doesn't have that, right? If you're parallel or the same slope as the edge of the cone here, or the slant height, you're only going to intersect the top of a double cone. Okay, I have a double cone. So a circle, also too, likewise, if you're parallel to the base of a cone, so we have a one cone resting upon the apex of another cone, right? This is a common math diagram you'll see later. Like, what the heck is this? But anyways, if you're running a plane parallel to one of those bases, and you don't intersect, you intersect somewhere else that's not the apex, right? You're going to get a circle, and only one circle. You're not going to get two with that plane. Okay, run a plane through that's just going to intersect the lateral surface here, but it's not parallel to the base. You're going to get an ellipse. So you'll get an oval as the intersection of that plane and the cone, or the double cone, right? You just get one oval. Okay, double cone here with hyperbola, if your slope is steeper, right? If you're going through the actual one of the bases here and you have a steep slope and you're going through, you're going to go through, yeah, unless you're going away from the actual top cone, for instance. If you're doing like this here and steep, I suppose that would still be a parabola. If your plane's kind of going like this would still be steeper than the slant height of the cone on top, but it would only really intersect the top. Okay, so it looks like this plane is going more like this. It's going more like this, and it's intersecting the top cone and the bottom cone, and kind of these almost parabolic looking shapes. Another thing that kind of confused me in high school too when I was studying the first time, like, what's really the difference between a parabola and a hyperbola? They both look U-shaped. This looks like an upward shaped U. This looks like a lower shaped or downward facing U. Okay, and on a graph, right, a hyperbola might be going left, right. Believe it or not, it could be going up, down too. It could be going up, down too. And then, as we all know, parabolas can go up. They could go down. There's only be one of them on the graph. Parabolas actually can go sideways too. Okay, so you'll study those later as well. Those will come up when you study conic sections. They could go sideways. So just because it's sideways doesn't mean it's a hyperbola. It could be a parabola as well. So, but you get two of them with the hyperbolas usually. Anyways, transitioning a little bit here, I also want to give you a little bit of a background on why I have these PowerPoints already set up and when I go over these, because it's not usually just like somebody says something in class, I'm like, oh, I feel like we can talk about those a little bit more. So I have these PowerPoints because usually how I finish the year is something that I'm not going to have time to do with you guys. It's something called, and we'll get into a second. Actually, it's section 8.6. So remember, we actually did the first 5 sections of chapter 8, which was constructions. And then we skipped something that I usually say to the end of the year because, hey, it's just like, I think it gets overwhelming if you do it with constructions. If you do it at the end of the year, it's sort of like, oh, it's just something to think about. This is just something to like think about and suss out and sort of and ponder, I guess. And that's fine, right? I want you to be thinkers by the end of the year. So anyways, to get into this here, this is usually how I get into this with people. So we're really transitioning right now. Just bear with me. This does have to do with conic sections. We'll come back to that later. As a class, read the words you see below. Oh, yes, is the hardest question. I'd call on somebody. What's that top word, friends? What's that top word? Who's going to answer me? This one right here. The one that, yeah, you like, what do you mean top word? Oh, it's city. Okay, city. City, that's right. What's that second word here? Let's spin it around. I'm gonna call on you. I'm calling on you, Leanne. It's icicle, okay? It's icicle. It's not kitty. It's not icicle. It's not that. And then finally, I don't know if anybody's a fan of this 90s punk rock band from Berkeley, I believe. I believe they're from the Bay Area. What's that? How's that pronounced? And also, it's just a word. That's right, rancid, okay? So city, icicle, rancid. That's how you pronounce the CI with like an I after a C. And that's what we do. So how do you pronounce this word? How do you pronounce that word? And trust me, this is going to connect to conic sections soon. You pronounce it. It's not. Did you just say loci? Maxwell. Come on. How dare you, Maxwell? Loci? Are you kidding me? Oh, Raymond? You're saying loci? Oh, come on now. Come on now. It's pronounced loci. Okay, loci. So this is loci. This is plural Loci, plural for this word called locus, which I'll get into in a second. You're like, Mr. Ford, where is this going? Locust? That sounds like a bug, right? Doesn't it sound like a bug? Locust? No, you're thinking of locust. Locust. No, locust I'll get into in a second. Loci is the plural of locust. But anyways, that's what we're going to call this during these slides. Loci, not loci, because city, icicle, right? Sid, loci. Okay, loci. Anyways, I just need to get that out of the way before we hear the rest of it. Okay, so I'm going to go through section 8.6, which I normally do in a normal year. We're not going to have time, which is why when I email this out, I'm going to be like, this is totally optional for you to watch, and I'll even have the homework at the end too if you want to try it. Be my guest. It's a long summer here, right? Section 8.6 has to do with this thing called a locus, a situation of a locus, or situations of a locus would, situations plural would make it loci, okay, loci. So we're going to fill this in right now. So here is an alternate definition of a perpendicular bisector, okay, a perpendicular bisector. This is something to talk about here. Okay, so remember, a perpendicular bisector, right, how that's normally defined is that's the line that is perpendicular to a segment at its midpoint, okay? So you know that through not through a point. So through a point on a line, right? Through a point on a line, there's exactly one perpendicular that can be drawn. So if that point is the midpoint, that perpendicular that can be drawn, we're going to call that. We're going to define that as the perpendicular bisector. And that's a very useful thing to have because you can prove a lot of stuff with distances and make a lot of arguments from here, okay? There's another way of thinking about this, another way that people do define a perpendicular bisector, okay? Because a consequence of being a perpendicular bisector, which you could just define it through consequences. A lot of textbooks define things differently than your textbook does as they build out their axiomatic ways of working through and developing a science. But this could be a way that another textbook defines this here, is that a perpendicular bisector is the set of all points in a plane that are what? From the endpoints of a segment. What do we eventually learn? And we could just call us, just say, hey, that perpendicular bisector thing, that's the set of all points that are what from the endpoints of a segment. Are equidistant, okay, equidistant. So we know that, right? That was a consequence of being a perpendicular bisector. We proved it, but other textbooks might actually define it that way, I'm going to change the words for you here, just to hopefully show you what this other word means that I didn't have time to here. Okay, I'm going to adjust this, okay? So this thing called locus that I told you about, this is a way of changing certain definitions based on requirements, based on what do the points of a perpendicular bisector need to be? What points are we talking about here? So locus is a way of defining certain shapes, certain figures, right, based on the criteria that's required of the points of that shape, okay? So the perpendicular bisector, those points are required to be equidistant from the endpoints of a segment, okay? So a perpendicular bisector is the locus, so we could say the perpendicular bisector is the locus of points in a plane that are all equidistant from the endpoints of a segment, meaning the perpendicular bisector, right, all these points on them would have to be equidistant from the endpoints of a segment. But in order to be a locus, okay, so it's kind of like an if and only if thing, right? The perpendicular bisector is the locus of points in a plane that are equidistant from the endpoints of segment, right? So if they are the points that are equidistant from the endpoints of segment, and they're the only points that are equidistant from the endpoints of the segment, okay? So it's kind of like an if and only if. If you are equidistant from the endpoints of the center, then you're part of the locus. And if you're part of the locus, you're the only points that are equidistant from the endpoints. Anyways, I'm going to keep going on this one here. So anyways, the locus here, like this is just something that I normally do at the end of the year. And I'm going to tie this back, right? Guys, I'm going to spiral back to those conic sections in a second. A locus is a set of points satisfying a given condition or a set of conditions, okay? So it's a way of kind of defining something based on what conditions, right, it fulfills. All the set of points fulfill it. And they're the only set of points in the situation that could fulfill those points, okay? So if a point is in the locus, then we know it satisfies the conditions of that locus. And if a point satisfies the conditions of the locus, then we know that is in the locus. So this is sort of that if and only if thing, okay? So if we know it's in the locus, we're in the actual shape, right? So if we know we're on the perpendicular bisector, okay, then we will know it satisfies the conditions of the locus. So we will know that it is, for instance, equidistant because it's on perpendicular bisector. we will know it's in that locus of points that is all equidistant from the endpoints. And if a point satisfies the conditions of the locus, that means it's in plane. You got to be in the plane and equidistant, right, from endpoints. Then we would know that it's in the locus, right? It's in the actual locus itself, which is the perpendicular bisector. So a perpendicular bisector is a locus, right? It's a locus of points that satisfies something, right? Satisfies a condition, right? That you need to be equidistant in the plane, right? Equidistant from the endpoints of a segment. So that being said, right, it's an if and only if thing that we just kind of talked about. So hey, here's like another thing before we circle on back to, no pun intended, circle on back or spiral back. Spirals have nothing to do with conic sections, but circles do. Before we do that, going back to conic sections, let's just talk a little bit more about locus, because again, I skipped a section because I'm like, I might be like, why does this matter in the middle of the year? It's just cool, kind of cool at the end of the year that we have this the way of defining things geometrically in terms of what they fulfill. Okay, so question here: what is the locus of points in a plane 8 centimeters from point P? Let's think about that. Let's use our visual and spatial thinking or planar thinking here to figure out what that might look like. Okay, what is the locus of points in a plane 8 centimeters from point P? Okay, so let's say here, let me try to like picture this out. If we're 8 centimeters, let's say that this is 8 centimeters away. This would be a point, right? 8 centimeters from point P. Okay, where's another point? Well, it'll probably be like this here, over here, and then what else? I'll draw another 8 centimeters one, like right here. And what's going to be true about all these points? And I didn't draw this super carefully, but you catch my drift here, right? This is going to be a circle. Okay, going to be a circle, right? That would be the locus of points, right? A circle with radius 8. Okay, would be that locus of points. That would be in the plane 8 centimeters from point P. Okay, so written description is there, right? A circle in the plane. So you get an idea of like what this problem set might look like. It's just sort of like, hey, given this, what would our answer be? And you just write it down. It's not that hard. So here's a different one. This one definitely has anything to do with doesn't have anything to do with conic sections. So anyways, just another reason why I have this here is because circles, right? One of the conic sections there is a locus, okay, right? It's a set of points that are all equidistant from a fixed point within a plane, okay? What is the locus of points 1 centimeter from line K? Let's think. Ooh, Mr. Fortin, I remember doing this one last year. This one's savage. People are like, oh, I got it. Raise your hand. I got it. Super easy. Isn't it this, right? Isn't it this? What is the locus of points 1 centimeter from line K? You draw it in. I wish this were Kahoot. Be like, oh, is this the answer? Yeah, is this? Are these all points, right? So we draw a perpendicular here of 1 centimeter. That's 1 centimeter, right? This is 1 centimeter. Right, because you're congruent here because this is a line parallel. So is it there are 2 lines, not just one, but 2 lines parallel to line K, 1 centimeter away? Oh wait, hold on a second. We'll look at all points. It's got to be all the points to satisfy this. Oh, that's right. This is what you just did. What did I just say here? What you just did. Oh, then I went and drew it in. And then what the answer really is, okay, wait, this, I predict that you're going to make this mistake. You make this mistake every year, people. 2 parallel lines in the plane, each 1 centimeter from line K, on opposite sides of line K. Is that what you wrote down? Please be honest here. No, because that's not the answer. What's the locus of points? Come on, guys. What's all 1 centimeter's away? Oh, right. We forgot about that z-axis right there. We forgot about, the depth that we have here. So it would be a cylinder. And actually, would it be a cylinder? If you said cylinder, would that be specific enough? Let's see if I write in the answer here. A hollow cylinder, missing its bases, only the lateral surface. Right? You just say the lateral surface of a cylinder with a radius of 1. And that would be it, right? Because you could have points, coming an inch in front of the screen, and that would be 1 inch away from this axis, whatever it says here. Okay, so getting back to this here, why I brought this up in class, because again, I found this one of the more harder to grasp things, and kind of why we spend so much time on this thing in high school. So again, want to get you thinking about these things. Please have a heads up on them. Conic sections actually are loci. Okay, they all, and again, what are loci again? Or a locus of points. Okay, they satisfy a particular set of conditions for points in the plane. They satisfy criteria. Okay, so a circle, right? We just already have studied a whole bunch in geometry. So circles are in a plane, the set of points equidistant in a plane, set of points equidistant from a given point. What do you think ellipses might be? Can you think outside the box here? I'd be impressed if they actually tried to think about it outside the box and just came up with ellipses and kind of what makes them a locus of points. An ellipse is a locus of points. What might that be? What do you think? Well, let's see if I have it on the next slide here. So ellipse, okay, so a circle is the set of all points equidistant from a fixed point, which we call the center, in a plane, of course. An ellipse is just a slight variation of that. So horizontally, right, it has horizontal symmetry, it has vertical symmetry, but the vertical distance here isn't nearly as much as the horizontal distance. So it turns out the way we can define ellipse as a locus of points geometrically here is that it's the set locus of points such that the distances to a set of points, so like here, this point xy, the distances to this, to two, not one, but 2 points. The sum of the distances to 2 points is the same as any other point on the ellipse. Okay, so let me show you a different point here. Let's do point 2, and we'll do x2, y2 right here. Okay, this distance here, and I'll mark this like A, and this distance here, I'll mark this B. A plus B would be the same distance as this distance here from F2 to the other point here we're talking about, C plus D. Okay, so a circle is the set of points that are equidistant from a fixed point, known as the center of the circle. And an ellipse is the set of points that are a certain sum of distances away from 2 mixed points. And those points are called the focal points, right? The focal points, the foci, right? Foci, actually, I should say foci. That's right, the foci. Okay, so kind of more complicatedly written down here. Given 2 foci, F1 and F2, so it's just 2 points. Given 2 points, right? 2 points. So instead of a circle is given 1 point, and the set of points that are equidistant from that 1 point in the plane, a certain distance away, that would be a circle. So this is given 2 points, okay? An ellipse is the locus of points P, okay? Usually you name the locus of points. Hey, it's the locus of points P, right? Any P we have on here. This is a P down here, okay? P, and then this could be X3, Y3. And over here, right, this is another P. This is P, X4, Y4, and this here, such that the sum of the distance, they add up to a common constant, okay? So this distance here plus this distance here, right? I had to go above it here. Let's mark this E plus F. In this whole thing is F, right? So I'm going to put the F up here. E plus F would actually equal C plus D. Notice here that D is a little bit longer than this E here, but F is just a little bit longer than this C here. So they would actually add up the same thing. So that's why, you know, you get kind of close to F2 here, but you're pretty far away from F1. And it turns out that on a graph, it looks kind of like an oval, and it's in an ellipse. Okay, so it fits a locus of points here. Okay, so this another reason why this is important. Something to show you here is that this is actually something important to understanding interplanetary position, right? Ellipse. I haven't studied astronomy a ton, right, and gone into it deeply, but I did watch Apollo 11, the documentary that I showed you a few weeks ago, and they're talking about elliptical orbits, and they're talking about right, obviously orbiting a mass is important for interplanetary stuff, and if we're going to send more stuff up to space, we got the Space Force going on right now, after all, and the mega missile that dude was talking about, 45? I mean, who knows what I'm talking about here? Supermassive missile? Anyways, that freaking guy. Orbits, right? We orbit, planet orbits around the sun in an elliptical orbit. So the sun here is one of the barycenters. I forget what barycenter exactly means. Let's talk this up. I see it's or maybe it's barycenter. Get out here, barycenter. Astronomy, the barycenter is the center of mass of 2 or more bodies that orbit one another, and is the point at which the bodies orbit. It's important concept of fields in astronomy, astrophysics, and so that's sort of the foci here. Yeah, barycentric coordinates is the way we figure out elliptical positioning of mass. So this is Pluto. I don't know, New Horizons. Pluto Charon must be like one of the moons, a satellite, right? Satellite, kind of a moon, right, of Pluto here. That's that. So on the left, a planet follows an elliptical path around the sun, which sits at a focus of the ellipse. Okay, so the sun is one of the foci, let's say focus. And then we have another one here, which is another barycenter. On the right, two objects of a similar mass orbit around a common barycenter. So maybe that's the center. The barycenter is the center of mass. That might be different than what a focus here. Let's see. Barycenter, center of mass, the two more bodies. So I don't know how you figure out the barycenter. Calculator is a two-body problem. Anyways, yeah. Anywho, I forget what that means. There's a question for you here. Actually, this is a fun question. I wish I could ask you this in class. This is a good one here, guys. Who's going to tell me when's the Earth? Who's all this is a brain buster for you? I might actually put this into a Kahoot. I'm going to tell you this question because, guys, who's got me? When's the Earth closest to the sun, my friends? Guys, we're basking in the glow, the warming, glowing glow of the sun. When is it? When is the Earth closest to the sun, my friends? When? Who's going to tell me? Who's going to tell me? Tell me now. When is? You got to know this. Did you say it? Come on. Did you just say June? Did you say June 21st? Oh, you know where this is heading. That's not right. It's January. Check it out here. January. So this changes every year. It's not like super close to this, but it's usually in the first week of January. So think about it. Usually the way I transition this, I transition poorly. I was like June 21st. And then this is what I do. I say this. Well, June 21st, you're saying June 21st, that's when we're closest to the sun. Oh, I get it. It's like with the summer solstice or whatever. Sure, so we're basking in the sun's glowing glow because it's the summer. What about Brazil? What about Chile? What about Australia? What about South Africa? When are they closest to the sun? Is it still June 21st? But like I get it, right? We're tilted towards the sun on June 21st, northern hemisphere, but obviously that's not when we're closest to the sun because the orbit of Earth, right? The orbit of Earth is the biggest thing determining how close we are to the sun. So obviously, the Earth is tilted towards, right? Our axis, because our axis is tilted. Um, so when in the middle of winter, we're actually closest to the sun, but we're not getting as many the sun's rays aren't hitting us quite as directly, and that's the reason why it's more cold here. Okay, so this is a little bit of some action here. Looks like we got the moon orbit here. Some moon's orbiting us in an elliptical pattern, and we're orbiting the sun in an elliptical orbit here. So it turns out that we're closest, right? Obviously, the scale here, the tilt only brings us slightly closer to the sun, right? It's going to get more UV rays when we're tilted, and this is where we're tilted, right? We're tilted, our axes going around here, so we're tilted away when we're over here, and we're tilted towards the sun over here. But look, this is a much, much larger distance. Our tilt only gets us slightly closer to the sun, and it turns out in July, right, we are furthest from the sun, even though it's hottest here in California. Okay. Getting to more, another locus here is that you studied in Algebra 1. Here they are. Here they are again. Parabola. Okay, so parabolas, this is a little bit different here. Parabola defines as a locus, and this diagram is a little bit harder to follow here, but you got the idea of a focus happening into the last one with the ellipse, the focus, right? So an ellipse has a focus where two foci, two foci, where those are 2 points, right? So when we're talking about focus, we're talking about a point, okay, a point. So focus is going to come up in this example here. So with ellipse, you had 2 foci, and any point on the ellipse would be the same sum of distances away from those 2 points, okay? So this is different. You might be thinking here, well, what can I say about parabola? It turns out here's our parabola here, right? This is a parabola. Just on any parabola, you can actually do this. You can figure this out about a parabola. So the ones you've been studying in Algebra 1, you're going to go further on in Algebra 2 and into pre-calculus and whatnot. But you have a parabola here. A parabola is a locus of points that where each point is equidistant from a particular focus. Okay, so that's singular focus here, and I'll change the color. I'll change it to maybe green. Between a focus, which is a single point, it's the set of points that's equidistant to a focus, and a line, a straight line. That's right, a straight line here called the directrix. Called the directrix right here. Okay, so this is what this diagram is showing here: is that any point, right? So if you take this point here on the graph that they're showing, let's go magenta here. This point right here is the same distance from a focal point right here, a focus, which is right in the middle. And this will actually have real world meaning. I'll actually show this to you in a second. You can define a parallelogram, parabola through a given point and a directrix. Okay, so the point here is called the focus. I'm trying to work backward here. So we have this. We have a focus and then a line. So we have a given point and a given line being something called the directrix. Okay, and the actual locus of points that a parabola fulfills is the set of points that are equidistant from the focus and the directrix. So, for instance, right here would be a key point. What part of the parabola would this be? Oh, this would be the vertex of the parabola sits perpendicular from the focus to the directrix, halfway in between the midpoint of the perpendicular to right from the focus to the directrix. The midpoint to the perpendicular to the directrix is the vertex of the parabola. And then right, a parabola, if we do half the parabola right here, we choose any random point, like one right here, and I'll change colors to go to green. This point here would be, if we draw a perpendicular down here, the same distance away from the focus. Okay, if I drew it accurately, if I drew it to scale. Okay, same thing up here too. We're moving away from the focus. Okay, this is a bit longer here, and away from the directrix. And then this is definitely not drawn super accurately, but I did my best, and hopefully you understand what I'm saying here. Okay, so another conic section, and another way to define it as a locus of points. Okay, and this would be true over here. Look, this point is pretty far away from the directrix, but it's also pretty far away from the focus, and that should theoretically be the same distance right here. Okay, focus. Okay, so given a line D, right, known as the directrix, and a point F, known as the focus, not on D, a parabola is the locus of points P, whose distance from line D is equal to its distance to the line F. Okay, so obviously these distances are changing, but the thing that's staying in common is that the distance from the actual parabola to that given point and to that given line, known as the directrix, is the same. Even though it's going to be larger in certain places, it'll still be the same to the point and to the line. Okay, that is a parabola locus. Here's something kind of cool here. This is a non-Euclidean construction tool. Leonardo da Vinci created a parabolic compass. Yes. So a way of actually defining that locus of points. So, right, we have a compass, and what's that good for? What's the one that I gave you good for? Constructing what? Yeah, the locus of points equidistant from a fixed point. So there have been other challenges to create other ways of diagramming out and showing and constructing, proving that you have these other shapes here. So Leonardo da Vinci was actually came up with this, right? Obviously, one of the greatest thinkers ever. You don't even need me to tell you that. A way of using this idea that a set of points equidistant from a given point and a line results with a parabola. So a way of constructing that actually. Okay, and here's kind of a big one here with stuff you'll be studying in like physics and whatnot. Is about parabolic mirrors. Okay, so this is pretty important. They're using telescopes as a way to kind of redirect sunlight and redirect rays, right, that you're seeing into a fixed point, so you can observe kind of everything through a fixed point, known as the focal point. Okay, so this is big in like lenses as well too. Those are kind of parabolic, which we'll get to in kind of the next slide. But parabolic mirrors are using telescopes because it will reflect parallel rays of light to a single point. So we get those rays from the sun or something like that. They're hitting us. We can actually redirect that through a parabolic mirror into a fixed point here. And it gets super hot, right? If we're dealing with rays of sun at least. A circular, so we're talking in 3 dimensions. So this is obviously drawn out in 2 dimensions, but if we're picturing this 3 dimensionally, right? In 3 dimensions, right? The locus of points in 3 dimensions that's equidistant from a fixed point known as the focus and a line known as the directrix. So the directrix would be down here somewhere. That's actually something different. That is something called a paraboloid, which we'll get to in the next slide. It would not focus this way. It would be a paraboloid, not a parabola. And here, check this out. So paraboloids, you might have seen them in the world here. You might have one at home, how you get your TV or internet. Satellite dishes. Yes, 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 yes. Satellite dishes are paraboloids. Okay, so ways of creating radio waves and satellite waves down to that dish, and then gathering that, right? Gathering the information that it's getting from the satellites, right? Um, orbiting the globe, um, getting that information beamed back down, right? Would get caught, right, by this paraboloid here. Look, this is parabolic, right? We see here that the plane intersecting this at a perpendicular, right, would be a parabola. And if we take off that constraint that the parabola needs to be in one plane, all of a sudden it kind of looks kind of circular like this. Looks like a dish, right? And it's obviously called a dish. It's called a satellite dish. That's a paraboloid. And as parallel rays of sunlight come into that, or right information from a satellite dish, it's going to redirect that to this little thing that hangs out up front. This is going to be the focus between the ground. I mean, ground is in the directrix in this situation, but I guess I'm a little bit less familiar with what the directrix is here and why the focus is exactly located there. But that's what you have here. Okay, finally, hyperbolas. I remember learning this and like, why is this important? I don't really get this. But they are also appearing in nature. So remember, this is when you have a plane of a really, really steep slope, steeper than, right? This isn't very steep. This is a little bit more horizontal to the x-axis here. So it's not quite as much of a change in y from the x-axis as the plane. Right? It's not very steep. So this plane here is like basically vertical. It creates a hyperbola in intersects not just the cone itself, but also the reflection of that cone or the projection of that cone above it. So a double cone here. And this is naturally occurring, right? You can look around at home. Do you have any like lights going around the side? Any lamps, right? Set up a lamp next to a wall, and you look at the way the rays will project onto that wall. And this here isn't a parabola. These are actually hyperbolas, right? This here is a hyperbola. That's a hyperbola, and this here is a hyperbola. So it's sort of naturally occurring in light patterns. That's all I got to say about that. Okay, so you might be wondering, hey, Mr. Fortin, you've been talking about like foci, not loci again. Give me the loci? Give me the locus. What's the hyperbola? What's the locus of points for hyperbola? You talked about the parabola, right? That was the weird one with the focus and the directrix. You talked about the ellipse. That was the one where you had the two foci, and the sum of the distances to the ellipse was a constant, right? That's why it was equal to k. That was ellipse, and then the circle, of course, we all know that's the locus of points. It's equidistant from a fixed point, and these are all in a plane, right? These are all figures in a plane. If they're not in a plane, we got to say sphere, or we got to say paraboloid. I don't know what an ellipse is. I could easily look that up. An ellipse in 3 dimensions. Let's maybe look that up real quick. It's a nice thing about videos. I can go on as long as I want. Ellipse in 3 dimensions. What's that called? Let's see if it gives us a term here. Ellipse in 3D space. Ellipsoid. Okay, makes sense. Paraboloid, ellipsoid. Sphere is the one that doesn't really sound like circle at all. Anywho, there must be a hyperboloid for the one in 3 dimensional space. Hyperboloid is let's see what we got here. Yeah, there's a hyperboloid right there. So this is a design that you see quite a bit of. I'm trying to think of where I see that design. But anywho, this is a hyperbola, so this will be in just one plane here. Defined as a locus given two foci, f1 and f2. A hyperbola is the locus of points, such that this, you should probably say in a plane too, doesn't say this, is, right, hyperbola is the one where you're subtracting the y squared, or the signs are different between your x squareds and your y squareds. And anyways, we also have subtraction here. This is where you actually have two focal points. The focal points are located kind of in the same place, kind of like the interior of the parabola was on the last ones we just went through. It's in the interior of both of the hyperbolas here. Okay, so I still have this open in Desmos. You'd have like a focal point here, and a focal point here. And the absolute value of the distance, like this point right here, okay? And the absolute value of the distance from this focal point and to this focal point over here would be constant to like this to this focal point and this to that focal point. So, anyways, you're getting further and further away as you move up this hyperbola from both focal points. Focal point will probably be around here, but you subtract the distances and they're going to be the same. That's how you can come up with, right, given 2 points, right, given 2 points where you're trying to find like we got another point here is that's this distance to that focal point minus that distance, right? So it'd be like shorter than the two. We take the absolute value, and if we move further away from it, right, even though this is bigger, but we'd be subtracting that and taking the absolute value, so the result would be a constant. We should take the opposite value for subtracting. So, anyways, the heads up on that. That's just another thing that we have there for hyperbolas. Okie dokie. And this again will come up with the cosmos in the way of interplanetary positioning and whatnot, and other things we might want to do in outer space. So orbits can be circular, elliptical, parabolic. I feel like they're probably elliptical more than anything else, but they could be hyperbolic also. So comets, right? Comets are one where a super comet, Halley's comet, always really exciting. I don't know if you're in your lifetime there's really been a comet viewing, but that's always a big deal. Is going out to see a comet that would be visible from Earth out in the distance in the cosmos. So usually they're going in hyperbolic, the hyperbolic. Man, this is going so well that I don't know what to say, but hyperbolic flight path, I guess, hyperbolic orbit, I guess, rather than just orbiting around a fixed thing. So that's why with comets they come by not very often at all, and they're like harder to predict. And rather than us, we orbit the sun once a year, of course. You know that, right? Maxwell, Raymond, you guys know that we orbit the sun once a year. Hey, June 21st, 2010. How about that? This is a comet, right? The McNaught comet, I guess, may be visible from Earth. Who knows? But this is having this elliptical orbit. It's going through our solar system right here. So pretty neat stuff. Or at least visible from our solar system. We can't really tell depth right here. And hey, look at that, summer solstice. That has nothing to do with comets. Summer solstice has nothing to do with comets. Anyways, that's that. That's my talk. I was like, I had these slides. You were a little interested in them earlier, and maybe, just maybe, when you get to this stuff, you'll have a little bit more to look out for when you get to it in Algebra 2. So feel free to watch. Well, hopefully you have no choice now. Maybe you watched it, maybe you didn't, but hopefully you watched this and hopefully you got something out of it, something to think about here. Thank you very much, guys. Take care. Here's the homework that I usually assign after I do this, and feel free to give it a shot. Email me if you have any questions, or you don't need to email me. You don't need to tell me that you're doing this, but give it a shot. And if you really are curious about something, I'm happy to tell you how it goes. Take care. Bye.